welcome back, and today I'm going to show you how to prove this thing, which is the Shwarz inequality. And it says that the absolute value, if you take two vectors, u and v, and you dot them using the dot product, then the absolute value of this is less than or equal to the product of the lengths of those two vectors. And we're going to need a couple of things before we can start with the proof for this, this statement. And first thing we need to know is that this proof works over these vectors in real space, which is u and v are in some real dimension. So r2, r3, r4, something like that. In other words, these run u1, u2, u3, all the way up to u of n. Next, we need to know what the dot product says. So the dot product is u dot v, which is the elements of each vector multiplied together, and then we take the sum of those products. So we have u1 times v1 plus u2 times v2 plus all the way up to un times vn. And then lastly, we need to know the length of a vector. So the length of u is equal to the square root of each of the elements squared and then summed up. So u1 squared plus u2 squared plus all the way up to un squared. Or in other words, it's the square root of u dotted with u. And then later on in this proof, we're going to need to know the discriminant for a second order polynomial, which I've given here in green just to kind of give a recall of what the discriminant does. So it just states how many real roots p of x will have. And the discriminant for a quadratic, which is specifically the one that we're going to be using, is given by this delta symbol, and it's equal to b squared minus 4 times a times c, where a, b, and c are the real coefficients of a quadratic. And there are, quick reminder, there are 3 cases for this discriminant. It can either be equal to 0, it can be less than 0, or it can be greater than 0. Okay, so to begin with, we need to notice that for all t in the real numbers, I can take u plus tv dotted with u plus tv itself, and that this is going to be greater than equal to 0. And that's because we have these elements being squared, which will automatically make it positive. We've got the same thing happening among t and v, and then we have some kind of interesting behavior here in the middle. And if we take this particular statement, which is u plus tv dotted with u plus tv, and we FOIL this thing out, at least according to the rules for dot product, excuse me, at least according to the rules for dot product, we will arrive with u dotted with u plus u dotted with tv plus tv dotted with u plus tv dotted with tv. Make sure I'm writing all the parts out here. Is greater than or equal to 0. Okay, so next what we need to do is do a little bit of rearranging and using some of these facts that we've already established over on the left-hand side to make this thing into something that we can handle. Now, u dotted with u, if we had a square root symbol around this, it would simply be the length of u. And so u dotted with u with no square root symbol will give me that it is the length of u squared. Now in the middle here, I've got these two terms, u dotted with tv and tv dotted with u. And one thing that's important to mention here is that when, in linear algebra, we may or may not have commutation among the vectors, but since we're dealing with the dot product, which is just the element-wise products summed together, it doesn't matter whether I do this u dotted with v first or v dotted with u, they're identical to each other in the context of the dot product. So here I can add these two terms together. And I'm going to do a little bit of rearranging too. What I've got here is 2 u dotted with v times t. And then lastly here, we can notice that there are 2 t's being multiplied together, and then we have v dotted with v. And so v dotted with v, we can apply the same kind of reasoning that we did with u dotted to u, which is this is the length of v squared times t squared being greater than equal to 0. Okay. So now if I do a little bit of rearranging here, I can rewrite this, the length of v squared t squared plus 2u dotted with v times t plus the length of u squared greater equal to 0. And this is really nice because you might be able to see that these parts of this expression are just like our real coefficients in a quadratic, which looks like this. So here we have the length of v, which is a positive real number squared, that represents our a coefficient. I've got u dotted with v times 2, which is our b coefficient. And it should be noted here that from the assumption this is positive. And then the length, which is a scalar, and also positive of u squared, which happens to be the coefficient c. Okay, so let me quickly clean up the board and kind of summarize what we've found. I'll call this thing equation 1 here, but we're going to clean it up, move it to the top of the board, and then we'll proceed with the rest of the proof. Okay, so on the last board we found that when we take this kind of special combination of the two vectors u plus tv and we dot it with itself, we come up with this statement, which is the length of v squared times t squared plus 2 times u dotted with v times t plus the length of u squared is greater or equal to 0. And it should be noted here that we also said that this is a quadratic polynomial with a equal to the length of v squared, b equal to 2 times u dotted with v, and c equal to the length of u squared. So now we need to bring in this discriminant fact over here, and we need to recall that the discriminant has kind of 3 cases, and I'll draw them very quickly. In case 1, we have the situation where the discriminant is positive. And the discriminant being positive means that the polynomial here at some point has to be negative. In other words, it crosses this x-axis at 2 particular places. In other words, there are 2 roots. Now, case 2, you should probably know this is discriminant greater than 0. Case 2 is where we have the discriminant equal to 0. And in this case, we have our polynomial is going to simply touch the x-axis and bounce off of it, crossing in precisely 1 point, or in other words, there's 1 root to our polynomial. And then lastly, we have case 3, and case 3 is the case in which the discriminant is less than 0. And in algebra, this is where we would get like the complex numbers and that kind of stuff, because we have a polynomial who does not cross the x-axis. In other words, there are no real roots to that polynomial. So very quickly, we need to decide which particular case we're dealing with for our discriminant. And it should be noted here that a, b, and c are all positive in our polynomial. And so we very clearly will not have to deal with the case where the polynomial is negative at any point on the graph, because all of our coefficients are positive. We're not even going to have to deal with that one at all. Now, secondly, it should be noted that if the discriminant happens to be 0, well, then that is going to imply that one of the vectors is 0 to begin with. And so that's kind of trivial. We're not going to have to deal with case 2, provided that we have a non-zero vector. So that means that we're sitting squarely in case 3. In other words, the discriminant should be less than 0. So we're going to take this fact and I'm going to write it at the top of the board. I'll clean it up and then we'll continue with the proof. Okay, so on the last board we discussed the cases for the discriminant, and we found that the case that we're dealing with, since our coefficients are all positive and we're dealing with non-zero vectors, is that the discriminant will have to be a negative number. And that simply implies that b squared minus 4ac, the definition of the discriminant, is going to be less than 0. Okay. Now, rewriting this statement of the discriminant being less than 0, we come up with b squared less than 4 times a times c. And now if we substitute our values for a, b, and c back into this statement, then we have that b, which is 2 times u dotted with v squared, is less than 4 times a, which is the length of v squared, and c, which is the length of u squared. Now we should note that this is 4 times u dotted with v squared less than 4 length of v squared length of u squared. And this is very nice because the 4's are going to cancel out on both sides of this inequality, and it leaves us with something that we can very easily take like a square root of both sides to arrive with our final result. Now the square root of u dotted with v squared, of course, since this is the principal root, this is going to leave us with the absolute, wrong color. This is going to leave us with the absolute value of u dotted with v less than, and then the square root of the length squared is just the length of both of the vectors that we are using. And then it doesn't take much more to think about what happens in the case where we do have a 0 vector. And if we happen to have a 0 vector, then we can get that this is not only less than the product of the lengths of the two vectors, but it is less than or equal to the product of the length of the two vectors. And that is the proof.